All right, so the first reaction we're going to be talking about today is hydrohalogenation. So hydrohalogenation is an alkene reaction where the alkene grabs an H and a halogen goes and substitutes itself in the more substituted carbon. In this case, the alkene's symmetrical, so it's kind of hard to tell. However, the rule is that the carbon with more hydrogen in the double bond, that carbon will get the hydrogens. That's the key. So you have HX, the double bond breaks, the H and X just add across the double bond. Hydro, for the hydrogen, halogenation. You get a halogen and a hydrogen. Potential energy diagram looks very similar to an SN1 because you form a carbocation. That means there's potential that there could be a shift, either a methyl shift or a hydride shift. And I talked about beta carbons last video. Once that carbocation forms right here, you look anywhere, one single bond away, you can see if there'd be a hydride shift. And if there can be, there's going to be another intermediate. But really, the reaction diagram looks very similar to SN1. There is a carbocation intermediate, and yes, they do substitute after. In fact, the other half of this reaction really is SN1, just forming the carbocation slightly different. Because in SN1, your leaving group just leaves. Let's look at an example. This right here is not a symmetrical alkene. There is no line of symmetry. So which carbon in this double bond has more hydrogens? This one. So that carbon will get the H. I circled it right here. The other carbon will be positive. That's what we call Markov-Nikov's rule. The carbon with more H's gets the H. In other words, you always form the more positive carbocation, more stable carbocation. This is tertiary, 1, 2, 3. This would have been secondary. Can there be a shift? I look at my beta hydrogens. There are 3 here and 2 here. This is already tertiary. It's quite stable. Not going to shift a methyl or a hydride. So what happens is that my Br that's hanging out in the solution, because that my Br is not just a Br minus, can go ahead and attack top or bottom of that positive charge, which is why it could be wedge or dash. Since that's the only chiral center in my molecule, this is what we call enantiomers. Okay? So it attacks top and bottom of enantiomers. If there is already an existing chiral center, if there is an existing chiral center, if there is an existing chiral center, like here perhaps, oh, let's even start for you guys. Here you go. Okay. And that chiral center doesn't change, let's say. And you do the same thing. You grab the hydrogen, and which carbon gets the hydrogen? The one with more hydrogens. And you form a positive charge right there. Is there a shift? No, there's no opportunity for me to shift a hydrogen or methyl to make a more stable carbocation. My bromine's going to add top or bottom, wedge or dash. These are enantiomers if I covered that part. Because there's an unchanged chiral center, how we call it diastereomers. Okay? Hydrohalogenation. Double bond grabs the H. The carbon in the double bond with more H's gets the H. That leaves a negatively charged halogen, which is a good nucleophile weak base, if you watched the last video, able to go attack the carbocation. That's hydrohalogenation.